So the processor fundamentals, Von Neumann model 4.1.1, Von Neumann model. Remember, we also call it computer architecture or idea of stored programs. So early computers were fed data while the machine were running. It was not possible to store the programs or the data. That meant they could not operate without considerable human intervention. Think of a calculator. When you use it, you feed the data and then it works and then all it is gone. Neither your work nor the data remains. So in the mid-1940s, John von Neumann developed the concept of the stored program computer. It has been the basis of computer architecture for many years then. Remember, he just presented the idea, he wrote about it, and then his idea was taken by a couple of universities, they worked around it. He did assist them, but actively he never made the computer. The main previously unavailable feature of the von Neumann architectures were, number one, von Neumann architecture actually helps you to the processor. It was not there before him. Number two, processor can access memory directly. These are the features, all right? And computer memories can hold program and data together. That was the biggest feature. And the last, and that was most important, was actually the feature of stored programs. So stored programs, I told you that programs are basically collection of instructions. Means the program can now be written in the form of instructions and can be executed in order of the instructions. So the instruction, then instruction, then instruction, then instruction. All right. So what is the difference between data and program? Programs, when they execute, they take input, the process, and then they give out the data. So they consume data. While the programs are the collection of instructions. And data is what you give to the program as per the requirement. And then program processes. Now, few important things. The model itself. So let's suppose that this is computer's memory. Achha, let me make one thing very clear, that computer's memory is basically, whenever we refer to memory, we refer to actually RAM or the memory inside microprocessor. When I say the word storage, this is as per your syllabus, otherwise these are synonyms. When I say storage, so that means that permanent storage, where we can keep the data even when the computer is switched off. So get the idea. So hard disk, USBs and flash drives and external hard disks, so CDs and DVDs, they all are actually storage. And when I say memory, what I mean to say is RAM, or the memory, the RAM inside the microprocessor. Okay. So let's make a representation of von Neumann model, a pictorial representation of von Neumann model. Okay. So now, let's suppose that this is computer's memory. So let's suppose that this is computer's memory. All right, memory as in RAM, random access memory, where we keep the data temporarily. Memory has got two parts in it. The address part, every memory location has got the address, and the data part. All right, so let's suppose that this is computer's memory. There we go. All right, and this memory holds few of the instructions. Remember the instruction when we are studying computer architecture, the instruction solely refers to the assembly language, So whatever the instruction that I'm going to write over here are neither pseudocode or any other language, but the assembly language, which refers to computer architecture. We will study assembly language. Assembly language is basically the part of this particular topic. So LDD, let's say 56, add 57, increase, and then store at 58, let's say, and then we have got end. What are these commands? How do they actually work? It is let's postpone it, we will discuss about it. So let's say this first instruction LDD56 is placed at the address 50. This is 51. This is 52. This is address 53. This is address 54. Alright. And then let's say we have got two more addresses. And then let's say we have got 56, 57, 58 as well. Let's say we have got 10 placed at 56 and let's say 19 at 57. Okay, so now what is happening that I have depicted that how the RAM actually looks like. So if you look at the content, what is the content? This is the content of the memory. This content has two types. One is data, other is instruction. Alright, the first one is data, the other one is instruction. Now, if you look at these two boxes which I have made from 50 to 54, you can see that these are instructions. How do we know these are instructions? Because these instructions are in English and they look like instructions. Like this is load, this is add, this is increase, this is store, this is end. Over here, we don't have any instructions, just the data. So this whole thing is instruction. Okay, so it looks like that. This is instruction. So from address 50 to 54, these are instructions. And from 56 to 58, this is data. Alright, so these are instructions and this is data. The whole thing is called what? Memory. The last thing that remains is this. What are these? These are memory addresses or memory locations. Alright, so that is how your computer's memory look like at any given time, because it is only holding what? Program or their data. Alright, so then comes microprocessor. Microprocessor itself is made up of many things. Okay, and those things are inside the microprocessor are called what? They are called registers. But microprocessor is made up of, apart from registers, it is also made up of system buses and system clock and other things. Let's first discuss the basics. Let's say we have got one register called program counter. Program counter register is basically a register which holds the address of next instruction. It holds address of next instruction. Okay, so what basically happens as soon as you click a computer's program's icon, that program gets loaded to the RAM. You know what is the meaning of word load? Load means that you are bringing the program or the data to the computer's attention. And how can you bring the program or the data to computer's attention? By bringing it to, or by loading it to the computer's memory. This memory is actually the part of microprocessor, but it is kept outside microprocessor for two reasons. First reason is that the size of the memory is a bit large. Alright, larger than the processor. So let's say the processor is of the size of my a little part of fingertip, maybe let's say 1/4 of my fingertip, whereas the RAM module is bigger. So had they placed the RAM inside the microprocessor, the size of the microprocessor would have grown unnecessarily. So they kept it outside the microprocessor. The second reason to keep memory outside the microprocessor when it is part of microprocessor was the frequent need to upgrade memory. You want to change memory, you want to upgrade RAM. If I've got slower computer, the first thing that comes to mind is to upgrade RAM, because new programs, coming programs, what they do, they require more memory. So if the memory is full while the computer is running, the whole system becomes slower. Alright, we will look into it as well. So for these two reasons, they keep the computer's RAM outside the microprocessor. But remember that RAM is not a peripheral. It is peripheral are those parts which are outside the microprocessor. They are not part of the microprocessor, but they are under the control of microprocessor, whereas the RAM is a part of microprocessor. So what if somebody comes to you and say that, have you done that? And let's say it's a surprise for you. You would say that, how would I know that I would have to do that? Nobody told me. If somebody would have told me, I would have done that. So this is what the case for your RAM. Until unless it brings to your attention, until unless it is brought to your knowledge that you have to do something, how would you do that? So similarly, if you want to make your computer do anything, execute anything, take anything from you, bring anything from the disk, you have to tell it. And how would you tell it? By having the program which actually makes the computer do this. And that program needs to be loaded. Now there are few words: load, upload, download. Load means that you are loading the program or the data from your local storage. Upload means that you are actually transferring the data from your computer's RAM to another computer's RAM. That is upload. That is not necessarily just this internet. This might be another computer in the same lab or same arrangement where your computer is, and these two computers are connected over, that's a local area network, and you are transferring data from your computer to that computer. Does not mean that it is going to their hard disk or USB drive directly. Rather, it is being transferred. Download means that you are bringing the data from another computer's memory to your computer's memory. Let's say if you are watching YouTube. So YouTube server first loads that video to its RAM and then transfers that data through internet to your computer's memory. And then from that memory, the data is used and you watch the movie or whatever. So similarly, that is a download. Alright, so let's say that you are actually accessing the DVD drive from another computer which is connected over the local area network in the same computer's lab where you are sitting. So that is downloading as well. So that particular computer is making use of its DVD drive, loading the data to its RAM and then transferring that data from its RAM to your RAM. Okay, so that is download. Whatever, when the word load comes up, it only means one thing, that the data or the program is brought to the notice of the computer so that computer could use it or execute it. Alright, so when the program is loaded, let's say this is our program, a little chota mota program which has got 1, 2, 3, 4, 5 instructions. Now the computer's memory is vast ocean. You never know that where your program will be loaded. You never know that. When at first the whole thing started, it was always the same because you had no chance of multitasking. Nowadays, when the program is loaded, you have no idea that where the operating system will load it. Since few people have got 2 GB memories, few people has got 16 GB memory, there is a vast difference between the amount of memory. These memories, as I said, that they can be changed, their size can be changed. So where the whole program will be loaded, we don't know. Only when you ask the computer to load the program, operating system decides then and there where to load it. So operating system first looks for the empty memory and then loads the program. So it is not predictable that where the program loads. So if the program is loaded somewhere that computer does not know, computer cannot execute it. Like we are actually connected to our minds. Computers are not connected to their minds as in memories, as in RAM. So operating system's duty is to tell the microprocessor where the current program which has just got loaded is present. So how would operating system tell? Operating system will load the program and the first instructions address. Let's say for this program, the first instruction address is 50. That 50 will be loaded to program counter. That is why I said that program counter holds the address of next instruction. So program counter holds the address of next instruction. Next instruction is always the instruction which will come up after this particular program. What if you interrupt a program and we load another program? So the current instruction would be of the current program which is being executed. The next instruction would be the instruction of another program that will be started execution. So this current programs which is just loaded, how would computer know? Computer will put the data inside the microprocessor. How? By putting this address of the first instruction which is just loaded to PC, and that address is 50. Alright, that address is 50. So now the processor know where the first instruction is found. From this first instruction, which is in PC, it goes to MAR, memory address register. Memory address register. Okay. So what is memory address register? Memory address register, MAR. It holds address of current instruction. It holds the address of current instruction. Which is current instruction? The instruction which is now being executed. What is next instruction which will be executed? So from PC, the address goes to MAR. So MAR now has 50, which is the address of the instruction which now requires to be executed, not the instruction itself, the address. But first we have to actually deal with one contradiction. The contradiction arises when program counter says that it holds the address of next instruction, and the memory address register says that it holds the address of current. When they both are saying two different things, how come they both are holding 50? PC says that it is holding the address of next instruction. Next instruction is 51, not 50. And MAR says that it is holding the address of current instruction. So current instruction is 50. So if current instruction is 50, PC cannot have 50. It should be a different one. So what basically happens that as soon as the address is transferred from PC to MAR, PC increments itself by 1. PC increments itself by 1. So PC will now become 51. Alright, PC will now become 51. So PC increments itself by 1. PC will increment itself by 1. So now PC is holding the address of next instruction. Now you have to pay attention to this thing once again. PC always increment itself by 1. Because Von Neumann said that computers will be executing the program in the order of the instructions written. Means whatever the instruction that is written next will be executed. So by keeping that idea in mind, PC always increments by 1. If you want to change that order, you can. But by default, as soon as the address in PC moves on to MAR to become the current address, PC always increments itself by 1. There is no distinction to it. And for this reason, we call it sequential machine. Why do we call computer sequential machine? Because it executes the instruction in the order written, and that is always sequential, incremental order. So for this behavior of PC, we call computer sequential machine or serial machine. Alright. So now PC address is moved on to MAR, and MAR address is now the current instruction. Now what MAR will do, MAR will actually connect with address 50. MAR will actually connect to address 50. Why it would get connected to address 50? Because we have placed, the computer has placed 50 in it. So with the while that it gets connected to the computer's memory, the MAR, it is called address bus. Address bus. We call it what? Address bus. This address bus is responsible for taking address from the MAR to the memory or the other parts. So address bus. See, I have made arrow on one side. So address bus is unidirectional because there is no point. If let's say I want to make someone leave the seat and change the seat, I'll point out, hey, you get up from the seat and go to that seat. Alright, so what I'm actually doing, I'm pointing out that you get up from that seat and go to another seat. Alright, so I pointed out. So if I want to, I am the microprocessor, I want to access one memory location, I'm pointing out. Now what is accessing? Either to get data or to place data. If you want to take data from that memory location, you are pointing out that I need data from that location. If I want to put data, I'll be saying go sit there, or I'll be saying go save there. So in both of the cases, when the data is being fetched or placed, stored back in the memory, the MAR is always pointing out. Remember. So that is why we don't need the address to come back. Address is always pointed out. Okay. Now, how does this 50 reached out to the program counter? That is another bus. That is called control bus. What do we call it? Control bus. So control bus is actually not just for PC. It is actually responsible for other signals as well. Okay? So we will discuss about it later. So through control bus, the address of first instruction has reached out to PC. From PC, it goes to MAR. From MAR, it goes out to RAM as an address. Now, from that address, data or the instruction at that address arrives in MDR. So now it is MDR. MDR. Memory, data, register. MDR. Few of the books and websites also refer to it as MBR, memory buffer register. We'll talk about buffer later, but in short, buffer is the area where we keep the data until it is get utilized. Once it is get utilized, buffer is then used for another data. So that is actually what is happening with MBR. So sometimes it is called memory buffer register, BR. But that doesn't make any difference as far as the purpose of this MBR is concerned. All right, so now what MBR is holding? MBR is now holding LDD, what? 56. LDD 56. This is now the content of what? MBR. Now you need to understand that this content is actually arriving from the memory. Do not think that it is arriving from the data part only. MBR is having the data from the address mentioned in MAR. Okay, so the bus, the wire that is being used to send the data is called data bus. All right, what do we call it? Data bus. Okay, so it is not bringing from the part which is actually the data part. It is bringing from the part of the memory whose location is mentioned in MAR. Now there is a general confusion. People do write like from MAR it goes to MBR. Nothing from MAR goes to MBR with it. MAR points to that memory location, and from that memory location you might have either the data or the instruction. Whatever it is, whether the data or the instruction, that will arrive in MBR. That is the case. You need to mind it. Nothing goes from MAR to MBR directly. Rather what basically happens that MAR points to a memory location, whatever the content at that memory location. We know that either we have the data or the instruction at any given memory location. From that memory location, whether it is data or instruction, that arrives in MBR. In this case, we are specifically talking about instruction. Do not think that this bus is actually going to this address or this bus is actually going to this address. These buses are going to the memory. That's it. Not to a particular address. Whatever the address that you put on that bus, the data will arrive in MBR from data using data bus from that particular location. So this is actually just for your understanding that it is pointing to it, it's bringing back, but do not think that it is actually physically going to that particular location. So get the idea? So from the MAR holds address 50, that address 50 holds LDD 56, that is actually arrived in MBR. Do not think that these are two parts. This is the whole memory. This is the whole memory. Okay. I just made these two parts distinct just to make you feel that these are instruction and this is data, but we know that in memory anything can be at any location. So when MBR has got the instruction whose address was in MAR, that instruction from there now goes to another register which is called CIR. CIR. So what basically happens that the content of MDR, if it is instruction, it goes to CIR, and that CIR has now LDD 56. What does it have? LDD 56. Why does it have LDD 56? Because from MDR it goes to CIR. It's a common behavior. Do not think that there would be anything else other than this. No, it's a common behavior. As soon as PC has got something, PC will deliver it to MAR. As soon as MAR has something, that will be placed on the bus. As soon as that address will be placed on the bus will actually go to memory and will say that deliver the content of this address. And then computer would take the content of that address, in this case it is instruction, and place that over the data bus. As soon as that data bus has got something on it, that will be delivered to MDR. And MDR, if it is instruction, that goes to CIR. That is a common behavior. Now, CIR, current. Oh, we forgot to write the instruction. Memory data register definition. So it holds instruction at address in MAR. So whatever the address that is in MAR, the instruction at that address will arrive in memory data register. And then we have got current instruction register, CIR. So what CIR does? CIR is actually current instruction registers. It decodes and executes the current instruction. It decodes and executes the current instruction. Decode and executes current instruction. You have to write current instruction, right? It decodes and executes current instruction. So The cycle is now completed. Once this happens, CIR decodes and executes. Again from PC, as soon as that is done, again from PC, 51 will arrive in MAR. PC will become 52, MAR now points to 51, add 57 will arrive in MDR, from MDR it goes to CIR, add 57 will be decoded and executed. Now what is decodation? Decodation is like I said, let's say, my dear student, you bring me some water. Alright, so you saw that I'm pointing at you, you will then decode what you need to do to bring me water. So all that understanding and execution plan that comes to your mind, that how would I go, how would I open the glass door and I'll get out and reach out to that place where the water is, and then from that place you will fill the glass up and get back to me to bring me water. So that whole thing that comes to your mind, and then you execute it. So decodation is actually making a sense of the instruction and how that instruction will be executed, and then execution. Fortunately, all you have to write is it decodes and executes. That's about it. You don't have to, neither here in AS or nor in A2, that how the decodation and execution happens. No. All you have to remember is just this cycle. From PC, the address of next instruction goes to MAR. As soon as it reaches MAR, it becomes the address of current instruction. PC increments itself by 1 in order to have always the next instruction address. MAR then points out to memory with the address in it through address bus. From that particular address, the content, which is the instruction that arrives in MDR, from MDR using data bus. And from MDR it goes to PC, where the PC decodes and executes it. It is called fetch, decode and execute cycle. What do we call it? Fetch, decode and execute cycle. Now the part from PC to MAR to MDR, it is called fetch. So if somebody asks you what is fetch, you would say that address of next instruction from PC goes to MAR, MAR then points out to memory, and from memory that instruction arrives in MDR. And from MDR it goes to CIR, that is fetch. And then CIR decodes and executes it. But there is a little more part attached to it. We will discuss about it. So now let's complete the microprocessor first.